All right, I want to tell you what a triple integral is. So I'm going to start with a single integral, move to a double integral, and then sort of define a triple integral in the same manner. So let's review what happens with the regular definite integral from Calc 1. What you're looking at is a one variable function and some region in the domain. The domain here is one-dimensional, and we start by defining a Riemann sum over that region in the domain, which here is just an interval of numbers, a to b, on the x-axis. So what we do is we chop that region up into a million pieces, and we select a representative from each of those pieces, typically the left or right endpoint or the midpoint or something, and we use that representative, plug it into the function to get a height of a rectangle, and then we construct the area of each of the rectangles with that given height times the width of the base here, which is delta x, and then we form an estimate of the area under the curve by adding up all those areas of all those rectangles. That's called a Riemann sum, and the definite integral is defined to be the limit of those Riemann sums as the number of rectangles approaches infinity. So that is the definition of the single definite integral. The double integral goes in much the same way. Here, the difference is, of course, that the domain, instead of being a one-dimensional interval, we start with a region in the domain which is two-dimensional. So this is 1D, this is 2D. But the procedure is very similar. I take that region, I chop it up into a million pieces, and I'm systematic about it, right? I chop this two-dimensional region up into a bunch of pieces by chopping up the interval from A to B and the interval from C to D into a bunch of pieces. Then I select a representative from each of the pieces. I use that to determine the height of a rectangular solid by plugging in that representative into the function. So here is the height that I get. And then I multiply that height by the area of the base, which in this case would be like a delta x times delta y computation. I form a Riemann sum by adding up all those volumes of rectangular solids, and then the double integral is defined to be the limit as the number of those rectangular solids goes to infinity. And we understand this double integral to compute the net volume between the surface fxy and the xy plane. Okay, so I'm going from now a 1D domain to a 2D domain to a three-dimensional domain. So when I construct this triple integral, I don't have the advantage of being able to graph a three-variable function as I had with the one and two variable functions, but I can still inspect the domain just fine. So I want to take a nice region in the domain of a three-variable function, so I'm going to start with a rectangular solid. So I started with an interval in one dimension, a rectangle in two dimensions, and now a rectangular solid in three dimensions. Now I can't imagine this like 4D surface that is sort of hovering above this domain piece, but you can kind of just imagine, by analogy, that there is some, surface that I can't draw over this domain piece right here. Okay, so what do? I chop this up into a million pieces, and I do it systematically by chopping up an interval along the x-axis, along the y-axis, and along the z-axis into a million pieces. I go to each of those pieces, and I select a representative, and with that representative, I determine not really a height, but just some sort of W value associated with that representative through the function, and then I multiply it by the volume of the little portion of the region, like that. So from those computations, I'm not imagining this as like a geometric computation anymore. It is simply a function value evaluated at a representative of a small piece times the volume of that piece. I add them all up across the entire region of the domain, and I take the limit as the number of these pieces of the domain goes to infinity. And so the triple integral is defined to be this limit in the same way that the double integral was defined to be the limit of a Riemann sum, and so was a single integral. Okay, so now we're going to practice basically applying Fubini's theorem to triple integrals to compute them.